good to be here with you today. Appreciate the opportunity to come here to Weber State to the Sustainability Conference. Just going to present on the microhydro project that was designed and constructed in Smithfield City, Utah, Cache Valley area. Just a little background about myself. I'm a professional engineer, graduated from Utah State, my master's degree, and my company, I've worked, here in the state of Utah for the last 10 plus years, and my company was started back in 2009, and we we try to be the leaders in sustainable engineering and planning. We do a lot of sustainable planning, and this type of renewable energy design is exactly what we try to implement on as many projects as possible. Hydroelectric energy is something that's always been fascinating to me, and from the time I was a young child building little dams and stuff in the backyard. But I think when we think of energy, hydroelectric energy, we all think of the large dams, Glen Canyon Dam or Hoover Dam, Flaming Gorge, those type of size of projects. And for instance, Glen Canyon Dam, it generates 451 megawatts of energy, 710 feet high, 25 feet wide at the crest, and 300 feet wide at the base, and it releases a tremendous amount of water. Hoover Dam, same thing, 2,080 megawatt capacity, 3.2 million cubic yards of concrete. These are just massive scale projects. And I think it's safe to say that the days of large scale hydro projects are somewhat a thing of the past. I mean, with the environmental standards today and the costs and regulations, it becomes very cost prohibitive and not necessarily, I don't think it's very environmentally sound to do a lot of these large scale hydroelectric projects. And so, really small scale hydroelectric projects are an opportunity that all of us have to really utilize a really renewable source, which is water. This kind of breaks down, small hydroelectric power is generally projects with a capacity up to 10 megawatts. Mini hydroelectric is less than 1,000 kilowatts. Micro hydroelectric power is less than 100. And I think this is really the scale of projects that we can work with today as professionals. So this project in Smithfield Canyon, I had a client that approached me. We had about 700 feet of frontage along what's called Summit Creek of this canyon. And he came to me and he said, we only have roughly 20 to 40 feet of fall across this stretch of the creek. And he said, I'd like to do some type of hydroelectric project. And this is a little unique because oftentimes you either need, really high flow, maybe low fall scenario, or a tremendous amount of fall and low flow. But in this scenario, we had somewhat low flow and low fall. And so we kind of started, here's a picture of Smithfield Canyon. This is just north of Logan City, about 5-10 miles. So we started to do some planning. There's an existing home and a horse barn on the property. We began to kind of gather some data. Topographical data was the first thing. Water source, trying to find what the historical flow was, existing power usage on the property, to find out what they're currently using so we could size the system appropriately. And what we found when we did the survey is there was indeed about 40 feet of elevation drop. But the real issue was the property was split in half with an irrigation diversion. So we really couldn't capture all that 40 foot of elevation drop because of this irrigation diversion. And so what we did is we did an analysis of the property, and really the way it was using currently, we'll say in the next slide, about 18,000 kilowatt hours a year for the property between the barn and the house. The house wasn't occupied at the time. And so we decided to utilize Rocky Mountain Power's net metering agreement process and go with a project that would tie into the system, and with the net metering agreement, they would, whatever power is generated during the calendar year, they'd get a credit, and then remaining power would revert back to Rocky Mountain Power at the end of the year. Like I said, 18,000 kilowatt hours a year was the usage. And so we begin to kind of gather the data to size the system. The real challenge was the flow of data. There was not historical flow data for this section of Summit Creek. There was a flow, some flow data available in 1983, but in 1984 the flood took that system out. And so what we did is we did some in-stream flow monitoring in September and February, trying to kind of capture 2 different times a year where it's a fairly typical flow. And what we found is these are kind of the constraints. We had 18,000 kilowatt hours per year of usage. There was about 18 cubic feet per second of diversion at the irrigation diversion. The diversion is right here in the middle, right in the middle where this arrow is, so it kind of splits the property in half. What we showed is that there was a fair amount. The irrigation company indeed was using almost the full amount of their right at peak time of the year. And upstream of the irrigation diversion, we had 31 cubic feet per second in September and 16 CFS below. And so we had limited flow amounts. The February flow measurement was what we expected, about 6 CFS. So it was really a small amount. So what we did is we recommended to the client that we use these turbines. They're called ES&D LH1000. They're made in Canada. They are turbines that operate on low flow, low head situations. Each of these turbines can operate off of 10 feet or less of drop and can generate kilowatt of energy. And so for this is what we recommended 4 of these turbines for this situation. And so we developed 2 different concepts. The first one was upstream, the diversion, and there was more water upstream, but it also had some setbacks, some things that really we had to run more electrical wire with upstream location, which increased the cost. The second location was downstream of the irrigation diversion. You can see it right here in red. The diversion would be diverted from the stream, taken down through a pipe into the vault, and then put back into the stream. This had its pros and cons also. Concept 1 or location 1, like I said, it had adequate water, but also it needed a tremendous amount of wiring to get to the nearest meter. Concept 2, it didn't always have adequate water, but it had better proximity to the home where an existing meter was located. At the end of the day, we decided to use location 1 just because water is an important thing when you're talking about a hydroelectric project. You need water. And so 4 turbines were recommended to be installed, which had a generating capacity of 4 kilowatts or 96 kilowatt hours a day. So this project has the capacity to power 3, almost 4 homes, an average home in Utah. So I mean, it's a smaller size project, but it is very sustainable and offers a lot of opportunities for this property owner. So going forward, we begin the detailed design. Because it is a smaller scale project, there are no FERC permits that are required. We did have to get a stream alteration permit, and also a non-consumptive water right was approved by the Division of Water Rights. And then also just a typical building permit. The project was put out to bid in February of 2010. It was a good bidding climate. There was in the midst of the recession, and as the kind of the consultant, we acted as the construction manager on this project for the client. I always like this picture here. If you can see back here, this boat says change order, and I always thought that's really good. If you ever work with contractors, that oftentimes that's how they get their boats, is their change orders. And so we really wanted to make sure everything was included. It was $20,000 over budget what the client wanted to spend, so we kind of dialed it back, and took some components out that we could, to make it more cost effective. And at the end of the day, we select an electrical contractor, then also an excavator. So these are some pictures of the construction, which I think are an interesting part. We begin installing the diversion pipe. Here, it's a 24-inch PVC pipe, and as it started to go upstream, the diversion pipe, it slowly had more depth, and to the point that it was almost 12 feet deep at one point before it approached the vault. This is the vault where the water is diverted into this, the top of this vault. The turbines are located in this vault, and then the water is directed to the outlet. You can see the outlet right here at the base of this picture here. These are some of the valves and the T that was put in here. We decided to go with a precast diversion structure in the stream. It allowed us to really speed up the process of installation in the stream. We didn't have to pour concrete in the stream, which can be a real environmental hazard, and the state really appreciated our efforts on this. And so it came in two precast pieces. They slowly kind of diverted the stream around the first half of where the diversion structure was going to be located. And you can see here they're lifting the precast piece into the stream. That's the first piece installed, and then they started to continue diverting the stream. And this was right in about April, May. It was right before runoff started. We kind of hit a perfect time before the water really started barreling down the stream. This is the complete diversion structure installed. As you can see, there's a notch in the center of the diversion structure for the water to pass through. This here it's called a hydro screen. It's a stainless steel screen, small holes on the face of the screen that allows water to be diverted, but also keeps the sediment out. This is, a key component of keeping the water out of the turbines. So this is it with the system in operation. As you can see, it's coming over the diversion, dropping across the screen, and water's barreling into the vault. This is before the turbines are installed. Here is a top view in the vault. You can see the turbines. We only installed 2 turbines at this point. The turbines are installed in this metal vault or metal tray at the top of the vault, and the water is directed through the turbines down to the base of the vault. This is some of the electrical equipment. It was kind of with the electrical equipment, the manufacturers told us that there was, to their knowledge, no known grid tie net metering hydroelectric project of this type that they knew of. And so the electrical engineer on the team, he did a great job of really finding different electrical components that worked with the system and allowed us to net meter and put more power back onto the Rocky Mountains grid. So in summary, it's a direct tie 4 kilowatt hydro system, micro hydro. It took a lot of iterative design. There was not a lot of known projects similar to this out there, and to this point there are only 2 of the turbines that have been installed. This type of project is, unfortunately, I was talking to one of the people here at the conference today, and micro hydro is not incentivized, at least by the federal government or the state, and so it's a shame because I feel like it's one of the more renewable sources. Water is very renewable. So the ROI on a system such as this is maybe not as good as some of the incentivized sources of renewable energy. That's about it. Any questions? I'd be happy to answer. Yes. It was between 15 to 17 years without any incentives. It's someone, if you're going to do this type of project, you have to have kind of a long-term approach to it. Yes.
And you look at your ROIs and your flows. Look at any models for climate change, directly saying less. What do you think of that?
Yeah. Well, that's a good question you asked. You know, when we looked at the ROI, did we look at climate change, did we look at, you know, any models to determine there would be less flow? We didn't in this instance, and there was really limited data already in this basin, and so we kind of went with what available data we had. Thank you very much.